Okay guys, going to have a quick look here at the 2019 higher level engineering. So it's question 2. So A. So the design and manufacture of crankshaft in high performance sports cars must be taken into account, both metal fatigue and hardness. So describe the terms metal fatigue and metal hardness. So metal fatigue. Now they'll put it into context like with a camshaft, or they'll describe, you know, some machine part, but really they're looking for the definition of fatigue, and that's basically failure due to repeated cycles. So basically, and you could say, just explain a bit more then, so you could say a camshaft turns at maybe, you know, 6,000 to 8,000 revs per minute or more in a racing car. Now you wouldn't want to be driving your Micra or your Ford Focus at that kind of revs, obviously. Like, but so basically, metal fatigue anyway is failure due to repeated cycles and or say repeated loads. And the example I often give there is like in the testing of hinges there. So they would set up so hinges are tested to see how many million cycles, or so can you open the press door like 1,000,000 times before failure. Okay, so that's metal fatigue. Now the other one there then is hardness. Is the ability to resist wear or indentation. Now indentation is dots or little holes being pushed into it. So the ability to resist wear and indentation, generally on a surface. Okay, and you see, just to show you know a bit about it, you should say that hardness is often associated with brittleness. Okay, so materials that are very hard are often very brittle, e.g. cast iron and ceramic. That's like a sink or a toilet bowl, stuff like that. Okay, so that's hardness and fatigue sorted. Now, part 2 there then. So that's A part 1. So part 2, just leave plenty of space between them now. Don't go lumping them all on top of each other. So describe with the aid of a diagram. So they're looking for a diagram here. A test for metal hardness. So hardness test. Now how hardness test works is a sharp point is pressed into the surface of a metal. So hardness tests are done by pressing a sharp point into the surface. There are, and measuring, I'll just say, and measuring the indent. So there are a few tests. So you've got the Vickers permit, which is a 136-degree permit, and then there's the Rockwell ball and the Rockwell cone. So the Rockwell ball test presses a ball, so that uses a sphere, and Rockwell cone is obviously uses a cone, a pointed cone like that. Just draw it there, and a sphere. Okay, so there are a couple of different tests, to name a few. So it said to describe one, so now it said with the aid of a diagram, so pencil would be good. So I'll just freehand sketch here one of these. So basically you've got some kind of a machine that has a kind of a U shape like this, maybe a slope here for a display panel. So there's our machine like that. That'll do. We'll put it sitting on a surface. Like that. Now, colours would be good, I guess. But there's basically the the outline of our machine. Now, if you could, I'm not going to. You're better off unless you're good at drawing, to avoid trying to make that 3D, because a diagram is a diagram. So just draw something like this with a point up here, and down underneath you want to put some kind of a platform for mounting a test piece. So I'm going to just draw in here some kind of a, I'm going to call this the test piece. Okay, and we'll give it one or two buttons up here just to make it look all fantastic. Now, you could try doing that 3D, but I don't think it's worth the bother of it. So, and if you label that there, then so this is the display panel. And this is the indenter, and that would be the mounting table here. So that would do. Now, what you want to draw there then maybe is another sketch then beside it, just zoomed in on this here. So that would be, so I'm going to do this for being the Vickers pyramid test. So I'm going to just draw that there like this. I'm going to draw this is the test piece, and what you're trying to show there is an indent. So that's an indent, like a dot there. And if you were looking down on top of that now, if I draw this here like this, or indent, because that's a pyramid, the indent is going to be like this, a diamond shape. So you basically just draw a square with diagonals, really is what that's worth. And what you're measuring there is the diagonal here. I'm going to say D there. And I'm going to label this there now. So this is the so this is the Vickers. I should have probably done it up here. So this is the Vickers pyramid test. Okay, so this is a 136 degree pyramid point. So the angle there basically is 136 degrees, and the measurement, the last thing I want to just explain there is that the measurement is the diagonal of the indent. Okay, so that's very important just to highlight that. And the harder the piece, the softer or the smaller the indent. Okay, and I suppose what I should say there is that basically you just put the piece up there on the table and push a button, and the pyramid, it just comes down automatically and presses it there with a force. So that would do there for, there's a diagram. We've named it there that we're doing the Vickers pyramid test. Now I'm after going off there now and doing what I shouldn't have done there, is leaving no space and kind of squishing this in. It's not the best way to go about it. You know, I'd have been better off there to maybe even go to the back of the page. So there's our test. So I just flip that over there, guys, and I'm going there then to the second part there, which is is a stress strain diagram. So we've got a table there that you need to, you know, go online there and find, or go to your exam papers there to find the exam paper. But we've got a stress and a strain thing. Now the stress, like how big to make this there now. So like the stress is going up to 425. So 425. So you definitely want to take up a half a page nearly with this anyway. So if that 100, 200, 300, 400, 500. So that'll do really. So it's 100, 200, 300, 400. That would be 500. So that's enough in that direction. And in this direction there then, the strains there then are going up as far as 8 is the highest. So I'm going to go with maybe 1.5 for my distances. But basically I just want 8 equal distances along here, and I'll just, now in the exam you can use graph paper, which makes life a bit easier as well. But so that's going to be 1, 2, 3, 4, 5, 6, 7 and 8. And like I say there, you need to be looking at the information table there now to make sense of that. Now I suppose I could just pause it here and show it to you. No, I won't bother now. You know yourselves. So okay, so I'm going to plot this off. So for metal A, they said with a stress of 30 and, or sorry, 125 at 0.5. So at 0.5 it was 125, so I'll just draw a light line up there. So 0.5 it was 125, which would be the middle of that there. And then the next one that we had there is at 1, so I'll just put a vertical at 1. It was 260. So that would be 250, so it'd be like 1/5 of the ways up there. Now I wouldn't get too caught up on this, like it's not, you know, it doesn't have to be absolutely perfect, you know, once it's close enough. So the next one there then is 1.5. So method A is 400. And the last one there then is at 2. So I'll just label this actually that this is my stress, which is in newtons per millimeter squared, and this is my strain. Now the strain is the extension over the original length, but we're not that concerned about that either. Basically, you want to always have like stress over strain, setting this up. So the last one there for 2, it was 425, which would be here. Now you will notice that these are in a straight line, and it's important to notice that, and this one curves off. Okay, so there's a big elastic limit here, and I'm going to be talking about this in a second, I suppose, but like that's elastic there. Straight line means it's elastic. If you took away the force, it would go back again, and then when it bends around here and it breaks there, so that's what's called a brittle fracture. So it just snaps. So like that's probably cast iron, something like that. Now the other one there then, metal B, I'll use a different colour for this now because it'll make life easy to compare them afterwards. I'll use red for B. So at 0.5 it was 30, so that would be 50. So 10, 20, 30 would be around there. And at 1 it was 60. So again there, that's a straight line. If you're any good at maths at all there, you'd know like if it's a half is 30 and 1 is 60, they're the same proportion to each other. Then third one there, 1.5 was 87, 50, so the 90 would be there. Two then is 110. Now the next one there we have then is 3. Now A was broken at this stage, so we got figures there for 3 and 4 and 6 and 8. So 3, my measurement was 135. 135 would be around there. And 4 was 150. And 6 is 162, so 150. So it'll be around here. And 8 was 140. So now the start of this is a straight line. always check there for a straight line part in the beginning, and then the rest there then. So you can see in the second metal here you got a big massive stretch. So just to take this back one step there now, so like what was happening here now was you had some kind of a sample piece here. So this would have been tensile testing. So you would have had a sample piece with 2 dots in it for the gauge length, and just slide that up there. So you'd have a test piece here with a gauge length, and that's put into a tensile testing machine where it's pulled apart. So it took massive force. For A it took massive force and it suddenly snapped, whereas for B, which is the red one there, it never took much force. It just started, there was a little bit of elastic region, and then it just stretched and stretched and stretched away, and you would have got a what's called a ductile cup and cone fracture. So I'm going to label that there. That would be ductile fracture. So what did they ask us to do? They said to use the paper supplied, plot the diagram for metal B and metal A, and then describe with the aid of a diagram the type of fracture that will occur when A breaks and the type of fracture that occurs when B breaks. Now, where to do that there? Like, I mean, I think I could do it here on this if I wanted, because this is going to give us, you don't need to draw in all of the thing here really if you didn't want to, but I will put it up here. This would give you what's called a cup and cone. So you just draw this like the opposite of each other. So there's our test piece, like a dumbbell or a doggy bone or something like that, or a T. But so that's called a cup and cone. Fracture. So ductile metals give a cup and cone fracture, whereas brittle fracture then is different. I'll sketch another one over here. So here's our test piece. I'm just going to leave that out there for a second. We'll deal with the fracture in a second. So there's our test piece, and that will basically be just flat across here like this. And if you wanted to zoom in again on that, depending on how good you are at drawing there, you could kind of draw like a pretty flat there to say that that's pretty flat, fairly flat. Okay, so cast irons and stuff like that, they just snap across, whereas you get cup and cone fracture like this in ductile metals. So as I describe it, the aid of a diagram, the type of fracture that will occur when they break. Okay, so describe. So I'm just going to say there that like this was A and this was B. So I just want to describe there a little bit. So I want to say that A, it took a lot of force, and I'm just sticking in brackets there like 425 newtons Okay, so it took a lot of force to get a small extension. Okay, and then it snapped suddenly. Okay, so the big long straight line there, and like you could write pages on this, like, you know, not that you want to, but like you could say that it had a long elastic region, which is a straight line. And I probably could going to get my highlighter there, and I will just highlight that in here in yellow, and I'm going to highlight that's the elastic region. And I'll just do the same here with the straight line part of this here. It's definitely straight for the first two, I think possibly even three. So that's the elastic region here. Now basically it yields here then, and after it yields you've got the ductile region where it's just kind of stretching and getting narrower a little bit, more so by far on this one. So describe with the aid of a diagram the type of fracture that will occur when A breaks and the type of fracture that will occur when B breaks. So it had a long elastic region, which was the straight line, and it snapped. So we already said that there, and it broke or snapped quickly. Okay, so it was just out of camera there. I guess I might just raise it up a small bit. Okay. And then for sample B, then it had a short elastic region. That's this bit that I've highlighted in here. So there was a small bit of elasticity, but then it just stretched loads and loads, and then a lot of extension, stretching. So it must be a ductile metal. For example, copper. And this fractures, giving a cup and cone as shown above. So make sure that you tell them that you've drawn the cup and cone fracture above here. And they asked for a metal then that could be, so I was saying there, so that was a separate question. So one example of a metal consistent with A and 1, so you just say that A is possibly cast iron and B could be copper, aluminium, you know, or, you know, zinc, or any of the non-ferrous metals, really, the softer ones. Now the last part of that question there then, so the last part of that question there, it says non-destructive testing in NDT is critical in the design and maintenance of a wide range of components. So outline one application for each of the following NDTs. Okay, so we're looking at NDTs, which are non-destructive tests. So they want to look at one application for each of the following. Okay, so visual inspection, dye penetrant test, magnetic particles, and eddy current. Okay, so the first one there, visual inspection, is looking for surface cracks, obviously. But obviously they have to be big. Okay, now an example of that is aircraft wings. Okay, now the next one there, the dye penetrant is looking for surface cracks. So you spray or pour on the dye and wipe it all off and just run it under UV light, and that shows up cracks in the surface. But it would be much more magnified, or you would find smaller cracks than you would with a visual inspection. Now magnetic particles there is also for cracks at the surface. Okay, and that's on steels and irons, ferrous metals. And eddy currents then test non-ferrous metals. Like aluminium. For near surface metal defects. So a near surface defect would be, let's just say, there's a cylindrical bar or whatever, but if you chopped that in half, you could have a little void. If that was poured in a casting, you could have a void from an air bubble. Okay, so you could have underneath, so the surface looks perfect, but just inside somewhere there you could have a void from an air bubble. Okay, so that there is section C, part 1. And finally there then, the last one there then, just checking the question there again on this. Okay, so the last one there then, we were asked for one suitable X-ray method. Okay, so basically okay, so that last one there, one suitable, just checking there. So I was saying the last one there, that you could have an air bubble or an air pocket in under the surface, so it's inside in it there, and if you have an air pocket there, like, it's weaker at that point, but you wouldn't know it from looking at it. So the last one there, you've got an X-ray test. So as we should all know anyway, that X-rays show internal flaws without damaging the piece. So you basically want to show some kind of a X-ray emitter here, and I'm going to just put an object on this. Which I call the test piece. And I'll just put this up on a platform here. And what we want to show here then is X-rays. And maybe a good thing there then is to just put some kind of a readout over here, a display or something, a monitor. And it's just amazing, you find a flaw showing up here on our display. But the idea is that if there's a void here, an air pocket or a hollow inside in that there, that more rays will get through and you'll get darker spots on the receiving surface down here. And the sensors on this can detect that there's more X-rays getting through, which shows up in our X-ray display over here. So I'll just say that it's our display monitor. So what is coming through this here? So the X-ray there, just to describe the X-ray test there, that you've got electrons from high temperature cathode pass through the solid metal and show any defects. Okay, so now you could write more, obviously a lot more now, but again there, just to recap on that. So like really there we're taking like 1, 2, 3 pages to work through one exam question there. So you know, that's kind of an idea of, you know, to do well in higher level, that's kind of what you're talking about.